Alright guys, we are doing two types of problems today. Well, two problems. The first one, we are going to do dimensional analysis using metric system and distant units and time units. The next problem, or the second problem, we are going to use the mole and those conversions just to get used to working with those conversions. So in this first problem, we talk a little bit about Usain Bolt. He is considered the fastest man currently in 2016, as he won a lot of golds this year. Usain Bolt set the record for the 100-meter dash at 9.58 seconds in 2009. What is the corresponding average speed in units of miles per hour? At this speed, how long would it take to run 100 yards? Now, our goal is to make sure we're using dimensional analysis correctly. So start by simply saying, what do you want? Here we want his rate in miles per hour. They ask us the second question, and in the second question they also want to know how long it takes to run 100 yards. When they don't tell you a unit to answer in kind. If they gave us seconds, like they did here, then we're going to answer in seconds, just to make our life easier. We are given, that's our next thing, what are we given? That for every 100 meters, he can run that in 9.58 seconds. Well, for those of you who are in physics or were in physics last year, will know or recognize that as velocity. We have a change in distance over a change in time. For those of you who are not in physics, this is a simple rate. How long is it? How long are you, or how long does it take you to travel so long? So in order to figure out a rate, we put meters over seconds in order to figure out velocity, distance over time. When we calculate that, we get, if we want to calculate it, we can leave it the way it is if we want, but I don't want to, so I like to make my life hard, I guess. 0.0958 meters per second. Now that we have that, let's figure out a plan. We need some conversion factors. How are we going to relate the meter to the mile, seconds to hours, yards to meters, miles, all that jazz? So we need to figure out a plan. In order to do that, we need to know what are our relationships. For now, until you know what those relationships are, if you go to page A26 in the back of your book, you will find these relationships. So I know I'm going to need some relationship between meters and miles. Well, I know that there are 1,000 meters for every 1 kilometer. I know that 1 kilometer is equal to 0.62137 miles. And that should get me there. But in the second problem, I'm going to have to go from meters to yards, so let's go ahead and throw that one in there too. So for every 1 meter, there's 1.0936 yards. And then lastly, seconds to hours, or you can do seconds to minutes, minutes to seconds, or minutes to hours rather. But to save time, I'm going to say 3,600 seconds for every 1 hour. So now that we have that, let's kind of move that a little bit out of the way. Okay, so let's get started on the first one. Let's try to figure out how many miles per hour that speed is. So starting with our speed, because that's what we're giving, 0.0958 meters for every 1 second. Alrighty, so let's try to look at our conversion factors and see what we can do. So I'm going to take care of the numerator first. I need to change both meters and seconds. So let's take meters, okay? The meter is related to the kilometer, which is related to the mile. Well, that's where I want to go. I want to go to the mile. So in order to go to the mile, I've got to go to the kilometer. So let's get rid of meters. Now when you're doing dimensional analysis, it's all about placing the unit in the right place to get it to cancel out. So if my meters is in the numerator here, I've got to put it on the diagonal. So I'm going to put it in the denominator and the other conversion factor so that it will cancel out in the long run. So meters down there, and I said I was going to go to the kilometer. The bigger unit gets the 1, so 1 kilometer for every 1,000 meters. Looking at that, we get our meters to cancel, and now we're in kilometers. Great, grand. But that's not the unit I want. According to the problem, I want miles. So let's keep on going. So now I'm going to get rid of kilometers. So I've got to put it on the diagonal to make sure that it cancels out. Okay, if it's in the numerator here, then it goes in the denominator and the neighboring conversion factor. So let's go ahead and put kilometers down here. Now, I saw earlier that kilometers related to the mile, so I can go straight to the mile from here. So I'm going to go straight to miles, and according to that conversion factor, for every 1 kilometer, there are 0.62137 miles. Okay, well now our kilometers cancel. I'm left with miles. That's good, considering I wanted miles. So now let's take care of the seconds. Okay, to take care of the seconds, I'm going to set up another conversion factor. So now what do I want to get rid of? Looking at this, I see that seconds I don't want seconds, so I need to get rid of it. It needs to go on the opposite side. It needs to be canceled out. To do that, I've got to put it on the diagonal. So if it's in the denominator here, opposite of a denominator is a numerator. So I'm going to put it up there. So seconds goes up here. And I want hours in the denominator, so it's going to go down there. And I know that there are 3,600 seconds for every 1 hour. Well, looking at that, our seconds cancel, and I'm left with miles per hour. Oh, that was a bad idea. Now you can barely see that. Oh well. So what I would do here is I would pause the video and go ahead and calculate that. All right, so hopefully by now you've paused the video and your answer, you should have calculated, to 3 significant figures, and I'll explain that in a second, is 5.95 times 10 to the negative 5, and that should be miles per second. Now, a couple of things about this answer. It looks really, really small, and actually in the calculator, I think it comes out something like this. Now, you want to make sure that your answer makes sense. Miles per hour is a lot larger than meters per second. We know that because a meter is only like 3 feet versus a mile, which is, you know, huge. So it's a huge difference. So it should make sense that that is a really, really, really tiny, tiny rate in miles per, hour. So that should say hour, not second. Hopefully you're not laughing in the background. I'm sure you are. And you can answer like this or you can answer like this. It doesn't matter. I prefer scientific notation because it keeps my sig figs in check. I know it's supposed to be 3 sig figs. I said I was going to go over that. I know it's supposed to be 3 sig figs because if I look at my problem, that's 100. Trailing zeros count when there's a decimal. And then we have this 9.58, which are all significant. So there you go. All right, well, that's part 1. All right, so let's go ahead and tackle the next part of this question. I'm going to go ahead and erase this, so if you haven't written it down, go ahead and pause the video. I think that's not going to be hard. Let's see. Or maybe it is. All right, so now for the next part of this question. How long would it take to run 100 yards? Well, it's just a simple, easy dimensional analysis problem. So x seconds, right, because we want to know seconds, and we're taking 100 yards. And that's in scientific notation. You can leave it in scientific notation or write it as 100. It doesn't matter. Just note that there are 3 sig figs here. So now, once again, we're back to what do we want to get rid of? Well, we want to get rid of yards, but where do we need to go? It all goes back to that rate. If we look at our rate is in meters per second. Now we can do meters or we can go to miles, because now we have miles. I didn't even write it, but we have miles per hour, but let's just stick with meters, it's easier. So if I want to use this rate to convert to time, because this is the only relationship I have between time, all of these are distant units, except for this, but this time is not related to any distance. This is the only way I have, our rate is the only way, or our velocity is the only way can relate distance to time. So that's how I know I'm going to need to use that. So in order to do this, let's go ahead and cancel out yards. Well, ask yourself, how do you cancel out something? You have to put it on the diagonal. You have to cancel it out. It has to be over itself. So put it on the denominator, because technically right now, if we don't understand that concept, it's over 1. So currently right now, that's in the numerator. Now I want to go to meters so that I can use that velocity. So for every, according to this, for every 1 meter, there's 1.0936 yards. So for every 1 meter, there's 1.0936 yards. All right, so now our yards cancel out and we're left with meters. Great. I still want to get to seconds. So how do I do that? I have to find a relationship that's between distance and time. It sounds a lot like a velocity. So let's start with just focusing in on those units. What unit do I want to get rid of? Currently I have meters. It's in the numerator, so I need to get rid of it by putting it on the denominator, so it goes down here. Now, for seconds, to get to seconds, I'm going to put it on the numerator so that it can, be on top. We cancel out those meters that are gone. Now, how do I put in the numbers for this? When I look at the unit, it says 0.0958 meters per second. Meters per second. So that means that I'm going to go ahead and write it in, 0.958 meters for every 1 second. So that's where the numbers go. You write it the way you see it, okay? If there's something on the denominator, we assume it's 1. It's the same principle as doing this right here. So we have seconds, that's what we wanted, so let's go ahead and calculate it. Go ahead and hit pause and see if you get the right answer. So if you've hit pause and you've calculated it, here's your answer. You should have gotten 9:55 seconds. 3 sig figs because of our given information. I think you get 9:54.5 seconds in the calculator. Alrighty, so now we have more of a difficult mole problem, and I chose this because I wanted you to see something that was a little more difficult in terms of how to use the conversion factors. So this one says, what is the total number of atoms present in each of these samples? And the only sample it gives you, so it really should say sample. I pulled it from another problem. Obviously, there's more. So the only sample they give you is 150 grams of iron 3 oxide. So start the same way we started with the last problem, or with all problems rather. You're going to start by saying, well, what is it that we want? In this problem, we want to figure out what are the total number of atoms in that sample. What did they give us? Well, they gave me 150 grams of iron 3 oxide. Okay, well, let's make a plan. Okay, and this one you can't really use the appendix because you're not looking for any kind of distance, time, metric system kind of thing. I guess the mole is kind of metric-y, but what you need to use is your definition of mole and how you understand the mole to figure this out. For example, we know by definition 1 mole is equal to 6.02 times 10 to the 23rd atoms. We also know, because we have grams and we need the mole, because that's the only relationship between grams and atoms, is that we know 1 mole is equal to the molar mass in grams. Well, I can find the molar mass of iron 3 oxide relatively easy, and let's go ahead and do that just so we have that number. So the molar mass of iron 3 oxide. Well, there's 2 irons. Each iron has a mass of 55.85 grams per mole. And I'm being lazy. I'm not going to put that unit there just because I'm lazy. Plus 3 oxygens, that's 16 grams per mole. And don't give me a hard time. I know on my periodic table here it says 15.999, but I'm not worrying about that. Here we go. So if you calculate that, hopefully you paused it, you get 159.7 grams per mole. Well, great, grand. There's one more conversion factor here that we need to realize, and once again, you can't get this out of any book. You have to learn how to use your sight for this. You have to think outside the box. We need to figure out how many total atoms there are. Well, I know for every 1 formula unit of iron 3 oxide, if I just count out how many atoms there are, I can see that there are 2 irons and 3 oxygen, a total of 5 atoms total. So for every 1 formula unit, I have 5 atoms. That can be extrapolated to say that for every 1 mole of iron 3 oxide, I have 5 moles of atoms. Okay, I can say that because it's a ratio, right? If I'm looking at the micro scale, I can say, okay, for every 1 formula unit, there's 5 atoms. But if I'm looking at the macro scale and I start looking in moles, in terms of moles, I can bring that ratio up. It's a ratio situation. So now I have some conversion factors that I can use. Oops. So shrinking that a little bit to give me some room. Let's go ahead and start setting it up. So let's go ahead and use our given. We always start with our given. So I'm looking for X atoms and 150 grams of iron 3 oxide. Got a little carried away. All right, first conversion factor. What unit do we want to get rid of? Well, we want to get rid of the gram. Grams of Fe2O3. And where do we want to go? So here's where we have to look at our plan and see what we have. We know that the gram, the only thing the gram is related to is the mole. So obviously the only place it can go is the mole. So there we go, and it's moles of Fe2O3. Keep track of that compound. Do not get lazy. I know it's a lot to write in that little bitty space, but do it. All right, so for every 1 mole of iron 3 oxide, there's a molar mass in grams, and we calculated the molar mass to be 159.7 grams. So grams cancel, and I'm left with moles. All right, next, conversion factor. What do I want to get rid of? Well, I definitely don't want the mole. I want atoms, right? So we need to get rid of the mole. So moles of Fe2O3. Well, what can we do here? Let's take a look. I have moles of Fe2O3. This is just in general, 1 mole equals that many atoms. But I know that I can make this switch over to moles of atoms like this. So for every 1 mole of iron 3 oxide, I have 5 moles of atoms. So let's go ahead and throw that in there. For every 1 mole of iron 3 oxide, we have 5 moles of atoms. Well, now I have atoms in there. That's what I kind of wanted, but I don't want moles of atoms. I just want atoms, right? So now here's where we would use the definition of a mole, okay? I need to get rid of mole. That's the important unit to get rid of. We've already gotten rid of moles of iron oxide. Now let's get rid of moles of atoms, okay? So here we go, one more. Uno más, as they say. Now I want to get rid of the mole completely, get it out of there. Okay, and I want to go to just atoms. Well, like I said, use that definition. For every 1 mole of atoms, we have 6.02 times, or 22 rather, especially if you're trained by me, times 10 to the 23rd atoms. I know it's weird, but I can't fit it all there and all that jazz. Hopefully you're pausing it right now so you can calculate. Our atoms cancel, our moles of atoms cancel, and we're left with just atoms, which is the unit that we wanted. So now that we know what we want, or have what we want, we pick up our calculator. And when you calculate it, hopefully you paused it, you get a big, huge number. I'm going to go ahead and write these small. Here's a little tip for you if you're trying to carry numbers throughout a calculation. One way to keep track of your sig figs, but while keeping track of all your numbers, is to write insignificant numbers smaller or below the line of text. That kind of lets you keep track of the number, but also tells you that the only significant figures here are there. But when you write your final answer, make sure to write it correctly. 2.827 times 10 to the 24th. Oh, and never forget your units. Bam. And we're done. Awesome. Please review this as much as you need, okay? This is tutorials for you. And if you still don't get it, come in. All right? See ya.